right. So we're going to pick up with this part of the lecture, which I already went through, but I really I want to start you off at a broad level. So we will begin here. Cognitive science, which arose in the late 50s, the early 60s, as a reaction to behaviorism, which for a while dominated psychology and tried to approach human behavior as if all we needed to do was think about the stimulus and the response, and establishing those contingencies would allow us to fully explain human behavior, just as we can do with animals. Well, it turns out with animals, you can't fully explain their behavior in that way, and you certainly can't with humans. So in the 1950s, you had a lot of people that had been working in this paradigm that were trying to um, make sense of what happens between the stimulus and the response, and they couldn't do it without starting to postulate internal structures like knowledge structures, categorization, perception, memory. And so um, the field of cognitive science arose as scholars from cognitive psychology, well, at the time, from psychology, anthropology, linguistics, and computer science were all coming together and trying to answer questions about what is going on between the stimulus and the response. So traditionally, what cognitive science did was it emphasized simplified or symbolic stimuli. And that allowed them to really focus on the basic processes that connect stimulus and response, these internal mechanisms. So you use simple stimuli like this. For studying perception, the simplest stimulus is this Navon patch here. If you want to study something like mental rotation, you use this block figure. If you want to look at categorization, you might look at the categorization of colored shapes, red and blue squares and triangles, or you might have slightly more complicated things like these insects here, which can be decomposed in their features, but otherwise are quite simple. Now, the idea of bracketing emotional and social complexity was essential for control at this early stage. But beginning in the late 70s, and certainly by the time the mid 80s rolled around, we really needed to move beyond that. You saw people in cognitive science starting to look at emotion. And one of the things that you might want to do is look at, a stimulus, instead of categorizing purple and green squares and circles, what if we look at how well people can categorize expressions on a face? This is getting much closer to what the brain was really designed for. It's not designed for the cool reason of the laboratory. That's a very special case. So you'll often hear people talking about hot cognition. This is cognition in the wild in some sense, in which we no longer are bracketing emotional and social complexity, but we're letting it be a part of what we study. And it's a recognition that almost all of cognition evolved in circumstances where objects are not simple, they're very complex, they're saturated with emotion, history, and social context. And you want to, if you want to maximize your sense of how the brain works, how the mind works, you really need to be paying attention to the circumstances in which it evolved. So evolutionary psychology arises too as really a fundamentally cognitive phenomenon. Now, evolutionary psychology does a lot of different things, but um, one of the early things that distinguished it from sociobiology was a focus on cognition. So what is this social heat? Well, according to Robin Dunbar and his social brain hypothesis, the very existence of our advanced cognitive abilities was driven by our highly social nature. Dunbar has done some really impressive work showing that when you look at primates, As the size of their social group increases, that's what drives the size of the brain. We can make the case even more um, in a more detailed fashion by looking at things like working memory. Human beings have much larger working memory capacities than chimpanzees, our closest ancestors. And why do we need to be able to hold a bunch of things in working memory and juggle these things around? Well, Dunbar says it's because what we're really doing is we're holding social um, information. We're thinking about how another person thinks about another person's attempt to socially deceive yet another person. And uh, that kind of chain of intentionality, of intentional inference, is the kind of thing that you need a complex cognitive apparatus to track. We can also point out that in neuroscience now, um, when people aren't engaged in a task, then this part of the brain or a set of parts of the brain called the default mode network kicks into gear. And the default mode network seems to be driven largely by, I mean, we know this because we look at mind wandering studies. It seems to be largely focused on social problems and social cognition. So when you're not doing anything, what does your mind drift off to? Well, you start thinking about what am I going to do with my friends this weekend? How do I get ready for this date? Did I forget my father's birthday? And it's like our mind on default is trying to both simulate, represent, and predict all of the social things that are going on in our life. So, from this perspective, social sources of information, like signals in the human face, are a more fundamental kind of stimulus for cognitive science. And my career began when I was in cognitive science and I was doing word recognition with letters and words and other symbolic stimuli. And computers became sophisticated enough to start showing more complex stimuli like images. And so my very first research was to move from word recognition to thinking about how we can do this with something that has a meaning, but it's a different type of meaning. It's not conveyed by how we relate a string of letters to a set of ideas. Let's use the exact same methods and look at how we deal with something that's phylogenetically and ontogenetically more fundamental, like the human face. And from the beginning, many of us in this area were recognizing that we could look at perception, we could look at attention, we could look at memory, we could look at judgment. And when you put faces into the mix, it's not giving rise to the kinds of results that you get with very simple stimuli. I'll show you an example in a little bit of how this angry face, this real angry face, generates very different results from this schematic angry face. We nevertheless want to use the methods of cognitive science by focusing on simple stimuli. They came up with really clean methodologies, and we want to use those methods. And one of the key methods we're going to learn today is signal detection analysis. So let's start with non-social cognitive task. This is a classic kind of task that you would get in the 60s or 70s in a cognitive psychology lab. So the task is going to be to detect a letter, and a letter popped up very quickly, and then it was covered up by this string of additional letters. Those letters are what we call a post mask. And the reason we put that up there is because some early work discovered that if you just show something and then take it away, there's an after image that lives on the retina for about a quarter of a second in what's called iconic or sensory memory. And so you can't show something for 50 milliseconds and get clean performance, a clean sense of what we can pick up in 50 milliseconds if you don't replace the image with something else. So I'll do this again. We'll go back. So some letter pops up, right? Was it a D or a P? Well, if I ask you that, I'm tricking you because actually it is a phi. It's a letter that we don't use in the alphabets that most of us use, though if any of you are uh, familiar with Greek, you probably did recognize it, or maybe it's in Cyrillic too. The phi symbol is really like this D and this P conjoined together. And so I often use this in my classes because most people guess it's either a D or a P. They're trying to fit it into their expectations, and they don't perceive what was actually in front of them, which is a novel letter or figure. So this is a discrimination task. And one admittedly where I've thrown a little trick in there, but let's say we were looking at D's and P's. You're not only having to recognize a letter, but you're having to discriminate it from another kind of letter. And you also expect that it comes from a limited set of possibilities. Here I violate that expectation because this is what I actually showed. But in my classes out here at Arizona State, I'll do this even faster, and people will be convinced that they saw either a D or a P afterwards. Um, and so why is that? Because how we perceive the world is often constrained by what we expect to see. So what are some influences on the ability to discriminate something, the ability to see a phi versus discriminate it from the kinds of letters that you might expect, or the ability to discriminate a D from a P if we're doing this task with no unfamiliar letters? Well, influences on discriminability can take a lot of different forms. So there, we were looking for a letter. We'll try that again. This is actually a legitimate letter. So I think I've got the timing off on this. I can certainly see it. Maybe you saw it too. That was an F, our version of phi. So one of the things that's going to influence your ability to detect this is the signal strength. The amount of time that I leave it up there is one aspect of the signal strength. Um, the quality of the post mask. Well, that gets into a bit more subtlety about the design of experiments. But indeed, if I used a post mask that was a bunch of gray letters, then the black letter would still linger on your sensory memory. So you have to think about the quality of the mask and many cognitive experiments. We won't spend too much time digging into this level of detail in the way that we cover things. But it's worth noting that a lot of cognitive psychology has worked out a lot of the kinks in how you cleanly explore questions like signal discriminability. And so if social cognition becomes something that you're very interested in, we always want to go to the original cognitive literature for a method in order to really understand what is possible in that method and how to design the study correctly. We also have other influences that really come from a top-down perspective, like expectations. What if we run people through an experiment where you're discriminating uh, F's from H's, and you start off by showing these for fairly long periods of time so people can easily do it. Oh, F, H, F, H. This is similar to what's going to happen in your Open Sesame um, tutorial. The discriminability task is easy. Sometimes you make a mistake just because you hit the wrong button. You're trying to go fast, but in general, you can do it. Well, let's say we show F far more often than H. Even if you don't tell people that you're doing this, eventually they'll build up an expectation and they'll start hitting that F button much faster. Sometimes H's show up and they still hit the F button. Usually those false alarms are going to happen much faster than they would if you were slowing down and being careful. So expectations can influence things, but they come from the top down, and they generally push bias around rather than increasing the sensitivity of your experience of um, the paradigm. You can also influence discriminability with things like costs and benefits, rewards and punishments. Um, and this gets us back to the very early days of signal detection theory. This was developed after World War II. And in World War II, a number of things happened that made it clear that detecting something wasn't just about the physical quality of the stimulus. Detection is often about the expectations, rewards, costs, and benefits that people bring into the system. And so if you recall, the United States got into World War II because Japan bombed Pearl Harbor. And when that happened, uh, there were radar operators in Hawaii who were looking at the radar screen, and they would often see the radar go off whenever a big flock of birds, like a flock of seagulls, was coming in. And so early on, these radar operators would see these flocks of seagulls. They wouldn't be able to discriminate them from planes. They would err on the side of caution. We don't want to miss planes coming in. And so they'd scramble their own fighters. They'd go up and they'd discover it was just a bunch of birds. These costly mistakes, which cost the fuel and, maybe pilots are put in danger, uh, over time, they led to bias in the opposite direction. Oh, we just saw something on the radar. It's probably just birds. Let's not worry about it. And so the costs and benefits affected how the radar operators perceive things. And we did pick up on the fact that something was coming in, but we missed the fact that it was the signal that we were looking for. And so problems like that required a different way of thinking about a signal discrimination task that allowed the biases of humans, and nowadays we can think about the biases of artificial intelligence systems, to also be incorporated in our understanding of how signals were being discriminated or detected. So I gave you an example of a very simple stimulus, but what do we do this? How about we do this with social signals? So imagine you're walking in a city at night and someone approaches you from a distance. What do you detect? The first thing you're going to detect is probably their gender and their age. It turns out that we can detect a lot from the way a person walks. We can generally discriminate male from female. Not always, though. You can make mistakes, particularly if somebody is very good at emulating the walking style of the gender that they were not assigned. Um, you can also tell age. You can really discriminate between whether this person seems young and athletic versus someone who's stooped over and moving slowly and is old. So let's say the first thing you pick up as this person's walking down the street is that they seem to be a young male with an athletic build. If you don't know anything else about them, that's probably going to start giving rise to some trepidation because young men who are strong and physically fit do tend to be a little bit more dangerous than old grandmothers. Maybe the next thing you start noticing as they get closer are things like, even though it's dark, you might be able to pick up on the color of their clothing. You might be able to hear their accent. And you might be able to figure out that this seems to be someone who's a member of an outgroup. So a young male with an athletic build and also an outgroup member. Now your trepidation is growing into fear because historically, young men of the outgroup are much more likely to be people that are going to be dangerous to us. If we're walking around the savannah in Africa 300,000 years ago and we see a stranger coming through the jungle and it's a young male, well, that's generally not a good sign. Most tribes are Maybe tribes get along, but especially if it's somebody who's wearing a different color than you, um, that's a sign that they come from a different group, and there could be group conflict uh, that is either ongoing or could easily arise. When you go to East Africa, for example, um, ethnically, racially, the Samburu and the Maasai are very similar, but one group, at least historically, would wear red and another group would wear blue, and that would allow them to see across a vast distance, up, this person approaching is a member of my tribe, or this person approaching is a member of another tribe. I'd better make sure that I've got my club handy. So let's go back to our dark street. If you have pre-existing ideas that physically strong males are also likely to be aggressive, those pre-existing ideas could come from just social conditioning. Maybe there's no truth at all to this. Maybe it's just that you grew up with a redneck uncle who doesn't like physically strong young men of a particular group. But it's also possible that there's some deep-seated evolutionary reasons why. Maybe we just have a heuristic that says when you see somebody and you don't know who they are, if they're masculine, err on the side of considering them dangerous. That could be some program that we've got deep in our system. So disentangling socially learned and evolved sources of these biases is going to be very interesting. So, to go back to this, if one has pre-existing ideas that physically strong young males are also likely to be aggressive, one may accordingly infer that the person represents a threat and cross to the other side of the street. However, if the individual suddenly begins to whistle The Four Seasons by Vivaldi, now this fits with the fit with the pre-existing category of the aggressive young man is reduced because an aggressive young man isn't going to be whistling Vivaldi. And so the feeling of threat subsides. This is an example that one of my colleagues from our lab here, who's now at Toronto, Becca Neal, used, but it was based on a story of an African American male in Chicago who was well aware that white uh, suburbanites were often afraid of him. And so he adopted the habit of whistling Vivaldi as a signal to them that no, actually, I'm not a threat. I like classical music, and that's something that you might like. And so this just gives a different sense. And this is a very interesting kind of thing, right? Why would a black man in Chicago feel compelled to do this? Well, on the one hand, it's because he knows that there's pre-existing stereotypes. On the other hand, it might actually even be a way of managing the perceptions of what he affords so that he's less likely to be profiled and confused for someone um, who might deserve more scrutiny, like someone who might be a gang member, for example. So, how do we do signal detection in the face of social threats like this? Uh, there's not a lot of reasons why you would be biased to see an F or an H in a letter task, but there's a lot of reasons you might be biased to see anger or happiness on a particular face, depending on whether it's in group or out group, male or female, young or old. We can use exactly the same methodologies that we use with letter detection or word detection or shape detection. And that's this signal detection theory. Many of the recurrent problems of our social life have sculpted us to be signal detectors. And this occurs both phylogenetically over the course of evolutionary history and ontogenetically over the course of our life. And detecting signs of social threats and opportunities really can be sculpted in two different ways, at least two different ways. One of the ways that it can be sculpted is a detector can be biased by the costs and the benefits. And so one of the things that might happen is you might increase your false alarm rate to maximize correct detections. If you're worried about aggressive, if you're worried about aggression as you see a person approaching, if they're a young male, well, maybe it's worth crossing to the other street and false alarming, even if they might start whistling Vivaldi, just because you want to minimize the misses of a dangerous male, um, or said differently, maximize the hits of detecting that it's a young male, even if there might not be aggression there. The other possibility, though, is that the signal or the detector can become more efficient. So the signal detection task can become better. And we say that we use the term sensitivity to refer to more discriminability. You might have an X-ray technician who looks at the X-ray of your lung to determine if a little spot on it is just uh, cyst or if it's some kind of tumor, right? We want X-ray detectors that are extremely good at discriminating cysts from tumors or in a mammogram. We want to be able to tell that something is a tumor versus just something that's benign because the next step is to go in and do a biopsy, and that has some medical risk. So we want to design systems and humans that are coupled to systems to be as sensitive as possible. And evolution has done this too. We as human beings are sensitive to differences in color of things that we're encountering in the environment in ways that a lot of animals aren't. Thinking like this has led Randy Nesse to propose the smoke detector principle. And we started talking about this last time. The idea is an explanation for why evolved systems that regulate protective responses often give rise to false alarms and excessive responses, apparently excessive responses. So when you get sick and you get a fever, that's your body heating itself up to get rid of something that could be a pathogen. It's quite a dangerous process, though. And, fevers can get too high and you can do damage to especially your brain if the fever gets out of control. So the body is excessively responding to something, but it's to um, even even if a pathogen is not going to kill you, your body overreacts to it because the risk of missing a pathogen that's going to kill you is great. And so this is a system that's evolved. If we have these biological systems that evolved in our immune system, why not in our social cognitive systems as well? Nessie talks about many psychopathological examples like OCD as an example of this. Person that's concerned about disease and washes their hands all the time has a system that's designed to help them avoid getting sick. It just might be overactive. And I also spoke last time about the fact that you can think about opportunities, not just risks, how men overperceive interest in potential mates while women underperceive willingness to commit and invest. And there's good evidence that this isn't just something that's socially constructed, that's a function of how society is set up, but that this is something that happens across societies and that it's an evolved part of how we think about social signals in the mating context. I will show you many examples from our lab where we use this signal detection theory and experimental designs to push people around in the social decisions that they make and not only bias them, but increase sensitivity. So let's begin with a simple example. I want you to detect pathogen threat, signs that somebody is sick. And I'm going to make this difficult by blurring the faces. Um, which is an ecologically valid kind of noise manipulation, right? In the past, we might see a flash of anger on a person's face, so showing something very quickly makes sense. But we also might end up, seeing a person at a distance, or we just got some water in our eyes and we can only see a blurry image of their face. And so, how do we pull information out whenever there's an impoverishment of the stimulus? It turns out in visual neuroscience, we actually have two systems to pick up visual information, and one of them picks up kind of a blurred bunch of information first, and that's a faster processing. So this also has some very interesting implications for the design uh, of our visual system more broadly. So here's a face that could either be sick or not. You see this face, and then you have to make a decision. Hit one button if it's sick, one button if it's not. And here you can see the underlying faces that I use in a study like this. So the one on the left is, I will often say unblemished and blemished because I have a couple of other ways that I describe these faces, um, as you'll see in a moment. So the one on the left is clearly like the normal face. The one on the right has been modified in Photoshop to look a little sick. Um, but what that sickness is coming from, is it a pathogen? Do they have COVID-19, or have they been abusing methamphetamine? Either one of these is a plausible interpretation. The task is simply to discriminate the unblemished from the blemished faces here. Now, when you see this face under uncertainty, under blur, there's an internal response that we put along this x-axis. We call that the evidence axis. And presumably the different faces that are healthy are going to generate one distribution of evidence, and those that are unhealthy are going to generate another distribution of evidence, and those distributions overlap. Like on Monday, we talked about heights. Clearly, the heights of men and women overlap. There are some short men, there are some tall women. And so here, there are some people that when they get sick, it's hard to tell that they're sick. There's some people that walk around, and even when they're not sick, they look like they're sick. So there's going to be overlap. So when we run a signal detection experiment, we give people a number of trials, a number of opportunities to make this decision. So maybe we first see a person that's sick, and we say that they're sick because the evidence is quite strong. Even under blur, they look like they're sick. And so we say, yes, they're sick. And because we were accurate, that's called a hit. We might then see a face that is healthy, and the evidence is quite low for sickness. And so we really easily and quickly say that person is healthy. That's called the correct rejection. But then maybe there's a person that looks sick, but it generates this internal response, this evidence that that they're not sick. And so here, you might make the decision not sick, but they are. So that's called a miss. And you might have someone who isn't sick, but for some reason, the internal response, the evidence axis generates a lot more evidence for this. And you say that that person is ill, even though they're not. And that's a false alarm. We do this a bunch over and over again, so we get a percentage of hits versus false alarms. The logic of signal detection is really that there's a signal and a noise distribution that overlap on this evidence axis. And if you're an optimal signal detector, you're going to place a criterion at this point that I've indicated here on the evidence axis, because that optimally allows you, if evidence exceeds that value, it allows you to have a lot of hits while keeping the false alarm rates low. This is called an unbiased criterion, and the measure of bias we'll use is something that we call C. And for statistical reasons, you'll see in a few minutes, an unbiased criterion is going to be 0, and then we'll call positive and negative biases. We'll define them in terms of the signal and noise, the hits and the false alarm rates, in just a moment. Now, in a task like this, let's say you just discovered that there's a new variant of COVID going around that's super virulent, super contagious. Well, that might bias your criterion. It might cause you to suddenly, now the costs of missing a signal become much greater. So you want to increase the likelihood you detect a signal. But what else happens? You also increase the degree to which false alarms are occurring. So when you bias your criterion so that you don't miss a signal, that means that you're going to increase false alarms. Now, another possibility is maybe you're someone who working on the front lines of this new pandemic that arises, and you start realizing there are subtle cues that really distinguish a person who's got this from someone who doesn't, and you start to learn those, and you become better at making this decision. Well, now you can end up with these distributions on the evidence axis, the distributions of signal and noise separating. Becoming more, the task becomes more discriminable. So even if we leave that criterion in the same place, now you're going to hit more often, or let's say you have the same hit rate, but you have fewer false alarms. Or if you optimize this criterion placement, you'll still have less false alarms, but you'll increase your hit rate. So that would just be sliding that over to the point where those two distributions intersect. So now I want to take a few minutes to ask you what factors might affect either criterion placement or sensitivity in a task like this, a task of detecting someone who's sick or not. Let's say you get on the metro and you got two places to sit and one person each one of these seats has two people on either side of it. What are the kinds of things that are going to go into influencing how you make the decision about where to sit? And so let me pause the display of this for a moment so I can see who's talking. I'll stop sharing for just a moment. Excuse me. What kind of things would affect signal discriminability?
Yes, I have an idea. I'm not sure if I fully understood the question, but maybe if I'm, for example, caring for an elderly person or I'm pregnant, then my hit rates will increase because I try to be more careful.
Beautiful example. Yeah. Yeah. So yeah, if you're caring for an elderly person or you're pregnant, so you've got this newborn, and then maybe you're going to be particularly worried about this. You want to make sure that you don't miss any people that are sick. Um, and so that attempt to avoid missing illness is going to mean that you hit very often, but it's also going to increase false alarms. So that pushes the bias, the criterion around. Excuse me. Um, what about the sensitivity, the separation of these things?
Well, if I'm studying medicine, maybe I get better at discriminating sick people from healthy people, and then my sensitivity would increase.
Boy, I hope that's how it works. Yeah. Yeah, that's one good possibility. But the pregnancy offers another interesting one. Um, you know, pregnant women, suddenly their sense of smell becomes much more potentiated. So if there's a signal of illness, they become actually more sensitive to detecting it. At least I think the science still supports that perspective. So there's all sorts of physiological things, but there's also training things that can give rise to this. Um, we're going to make the case in a moment that maybe even emotions can shift this around. So let's go back to the lecture, um, and I will proceed. Go. Okay, so oops, I meant to switch lectures. Sorry, give me just a moment. So now we're in now we're in lecture one. There we go. Okay. So now I want to talk to you about a different way to use these faces that we were just talking about in terms of disease detection. The same face was designed to look like it could either be an aggressive methamphetamine addict or someone who has a contagious disease. The difference in the way that you frame this, even though the physical stimulus is exactly the same, taps into two fundamental motivational systems. So, my lab at Arizona State University has done a lot of social cognition where we try to look at the basic social problems that our ancestors had to solve, like avoiding aggression, avoiding disease, and then finding experimental ways to show how outcomes differ when either of these motivations are aroused. So in this study, what we've done is we've used these same faces. Oops, hold on. There we go. So the task is still to discriminate between uh, faces that have been modified using Photoshop versus those that have been unmodified. And we did it with Asian faces, Latino faces, and Caucasian faces from the Chicago Face database. If your eyesight is good, you can see that I've got the unblemished faces on the top, and then the ones that are made sick on the bottom. And even at this low resolution, you can pretty much tell the difference. This, by the way, would be another way to do this study. Rather than blurring the faces, I can present them very small, and that mimics the ecological conditions of seeing somebody at a distance. We haven't done this study, but my guess is that you'll get similar results to what we did with blurring, though it's an empirical question. So, the task here is a manipulation. You're going to see exactly the same faces, but we frame the discrimination as contagious disease threat or aggressive methamphetamine addict. As a subject, you only see one of these conditions. So you're sitting in the experiment and you're really thinking this is about looking for meth versus this is about looking for disease. I've already shown you the blurring manipulation. Um, the nice thing about blurring is that the blurrier the face, the more those two signal and noise distributions start to overlap. So you can push around sensitivity, and very you might find that at um, low levels of blur, people can be quite sensitive. But at higher levels of blur, the sensitivity reduces. And then you could compare that with what happens when you see the face presented in the middle of the screen big or when it's presented very small. So you can compare across different types of noise manipulations to see if the same kinds of effects obtain. I want to note from an empirical standpoint or an experiment, as an experimental design principle, I'm often trying to do things where not only are items being manipulated in a way that can be framed as aggressive or contagious disease, but also that every face can act as its own control. So I'll generate two sets of faces, or two sets of stimuli. Person A will see this gentleman in his healthy looking face, even though it's under blur. And then a participant in the other condition, condition B, will see this individual with disease cues. And that way, even though each individual person is seeing each individual face in one variant, you can look you can compare how the performance on a face in its healthy condition versus its blemished condition. You can do a within items comparison, like we often will do within subjects comparisons. We can do within items comparisons that way. This is a subtle point, and I probably shouldn't belabor it in a class that's only going to be as short as our class, but it can yield really profound results. It's very important to think about this. And I wouldn't have known this if I didn't come out of cognitive psychology. So let's look at what the framing does. First thing I want to point out is that there was a big effect of blur. Um, and so we ended up focusing our analyses on a 3 pixel blur. Things look basically the same as you blur the face more, but eventually it just wipes out all of the effects because people couldn't tell uh, disease from non-disease faces. Um, so when we look at these less blurred faces, the 3 pixel blurred faces, we have evidence of a smoke alarm type bias, a smoke detector effect, like Randy Nesse pointed out. There's a tendency to false alarm to avoid costly errors. So what we've got here is we've got bias, which in the positive direction is a bias to say, yes, that person has the signal of either aggression or disease. What you'll notice here is that, first of all, female targets are in blue, male targets are orange. There's more of a bias for male faces than female faces. So we're more biased when we see the masculinity of a face to say that's an aggressive amphetamine addict, that's somebody who's got a disease. The other effect that you'll see is that in the aggression frame, there's a greater bias overall than there is in the disease frame. So that might mean that these participants are more worried about aggression than they are disease. Um, that difference is a really interesting, I mean, it's a very large effect. Um, and it's quite interesting because these participants are seeing exactly the same faces, exactly the same stimuli. The only difference is what they think their task is. Detect aggression versus detect disease. So the tendency is greater for male targets in both cases. I should also point out that I have all the participants in the top graph, but because we also were looking at race, we looked at the Caucasian or the white participants alone. They actually show an even bigger effect in an interaction. Um, and we could spend some time thinking about why that is, but we won't do that right now. Um, it also ends up being the case that um, the faces that were Asian were, so we did this in the early days of the pandemic, when people were still thinking that this was coming out of China, when our former and unfortunately current president was calling it the Kung flu. Uh, so you had a lot of bias against Asian faces. And here we see that that bias and the disease, in every case, aggression, there was a more of a bias to see aggression, except for in the Asian faces where the disease bias is greater. So that's one example of how you can do a perceptual, a signal detection experiment with perception. Are there
May I
questions?
ask you a question?
Sure, absolutely.
Oh, yeah, because I'm wondering, can't that result be explained because people are more confident in recognizing aggression, and so reporting that they can see it in a face compared to disease?
Ah, yes. So if people are more confident, um, then uh, so if they were accurate in their confidence, then what we should see is we should see people being more sensitive. And so you should see D prime, but not bias shifting around. But you're probably right. If people are more confident that they can detect this, even if they're not accurate, that confidence might come out as a bias. Um, my father-in-law at one point when I was doing some of this work, he was a person who was super confident about his ability to do these tasks. And at one point I ran him through something and he was certain that he did extremely well, but he had a false alarm rate that was close to it was like 40%. So confidence sometimes shows up as sensitivity if it's accurate confidence, but a lot of times what confidence is it's just a bias. It's a really good question. It's a really good thing to note. Um, I'll have to think a little bit more about whether we could manipulate confidence to answer your question more precisely in this study. Um, so let me give you another perceptual bias. This is from a paper that I had you read called Signal Detection on the Battlefield. So the task here is not to detect a face, but it's to detect actually just a letter, an E or an F. And this was what we said we described to our participants. This is an enemy insignia, E or F. And the task is to ignore the other social cues. So I show you a face. Here's a male face, and then there's a letter that shows up. One of these would show up, either E or F, very briefly, and then the face again. So it would really look like this. Face, something like that. And so your task is to detect a letter, and the letter itself doesn't change. What changes is the face that acts as a pre and a post mask. And we told participants it's like you're working a checkpoint, people are coming through, and you just get a brief glimpse of something as their jacket falls open that might be a sign of being an enemy or a friend. This is how we're framing it for subjects. So we're going to look at bias again here. Again, zero bias means no bias. Positive numbers are a bias to identify as enemy. Negative are a bias to identify as friend. So here, with faces that have Western garb on them, we saw a non-significant bias to identify them as friends, and when they were female, a significant bias to see them as friends. Now, this is a bias. This means that sometimes you were seeing Western females with the enemy signal and you were missing it. For Arabic males, like this gentleman, there's a bias to identify the letter that appears as an E as opposed to an F. So sometimes an F is showing up, but people are saying E. And there's a trend in that direction for the Arabic female, but it's not significantly different. So this is a bias profile in typical conditions. Now let's change something in the person. So I've already talked about the fundamental motives. Aggression avoidance is one of them. We can arouse aggression avoidance by showing people images of violence, which is something I did in the study that you ran through, one of the studies. Um, we can bias them by having them read through a narrative of being in a situation where they're under attack by some enemy. We can show them a movie clip from Black Hawk Down. Any of these things arouses a sense of aggression avoidance, self-protection, or fear. We can even use something like this scene from Silence of the Lambs, where it's a white aggressor stalking a white woman, and there's no cues about in group, out group, about Arabic versus non-Arabic. If anything, there's just a cue about masculinity versus femininity. So the data I'm going to show you actually use this as the manipulation, this movie clip from A Silence of the Lambs. It gets people afraid, and then this is what it does to their bias against Arabic men. It more than doubles the bias, does nothing to the Arabic females, and it actually makes a bias for the Western males that swings in the opposite direction. So we did this for the Army Research Institute. And the implication here is that when you're at a checkpoint and the more Western people are, the less likely you are, the more likely you are to miss signs that they're actually an enemy. We also had another condition in which we activated a sense of anger, and we got a different profile of results. But largely, I mean, the key thing here is that in the angry condition, you might think that people are going to aggress against, or they're going to see more aggression, more enemies in the Arabic females, but we see everything swing to friend except for the Arabic male, the outgroup male. So here we define it as Arabic. But then we replicate this with faces that differ by race, black and white faces. We see a similar kind of effect. We've done it in a lot of different ways. So it's not really black faces or Arabic faces or Lithuanian faces. It's any sort of outgroup, and it just depends on how your group defines in-group versus outgroup. So let's think about the logic again. There's a signal E, there's a noise F, and these give you a little bit of evidence, and then you take it away, and you, based on that little snippet of evidence, have to figure out which distribution the evidence came from. And if you optimally place your criterion, it's going to be here, and that gives you the best proportion of hits to false alarms that you can have. But also, when you bias someone with this fear manipulation, well, that can shift this criterion. And so now you don't have the optimal ratio of hits to false alarms, but you're not missing very many of the enemy signals. And the way that you do that is by increasing the false alarm rate. Now, if there are two things that we know from social cognitive research, one is that cognitive capacity is limited. We can't attend to everything. And then the other thing is that people are often very miserly with the resources that they do have. And so this opens up a new possibility that maybe some of these fundamental motivations might actually enhance accuracy as well by motivating us to focus more, use more cognitive machinery and processing, and do a better job. And sure enough, in this study, when we look at sensitivity, or D prime, which is statistically orthogonal to bias, so you can have biased performance and you can still have a shift in sensitivity as well. So when we look at these faces and the detection of the E's and the F's, and we look at our sensitivity index relative to the control condition, under self-protection, people are liberating more cognitive resources and they're more sensitive to discriminating E's from F's. Whereas in the anger condition, they become less sensitive. Now they're willing to make more false alarms. They don't really seem to care too much about that. But in the self-protection condition, that motivation, that fear-based motivation seems to allow people to, even though they're biased, they're performing better overall with all of the faces. So this just highlights the fact that these fundamental motivations, these evolved emotional and motivational systems, they can actually sharpen or blunt the social perceptual acuity, not only in this enemy detection task, but across a lot of different tasks. Now, what about the speed of decision making? Well, Donders back in the 1890s proposed using speed as a way of detecting differences in cognitive processing. In fact, Donders' method is it may be the first psychology experiment. And he developed something called the subtraction method. You can also call this chronometric or choice reaction time methodologies. And so this is used a whole lot in a lot of different ways. And when you're asking someone to make a decision about a face or a letter or a symbol, you can not only look at their accuracy in making these decisions, but also in how rapidly they can do it. So I'm going to ask you to name the emotion of on the face as fast as you can. Angry, happy, happy. Several questions arise in a task like this. Which emotion generates faster responses? That's one question you can ask. Turns out that happy faces are detected faster than angry faces. Which emotions are more accurately detected? And does the emotion on the prior face affect the response? That's called priming. What if I saw that happy face and it made me even faster to detect this happy face? That would be a priming effect. What if I saw that happy face and it made it easier for me to detect angry faces afterwards? That's called a contrast effect. Both of these can obtain, and we need to do studies to figure out which is going to happen. Now, I've already shown you these results from our JPSP 2007 paper, where it turns out that the sex of the face is going to influence both the speed and the accuracy. So angry men were faster and more accurate to detect. Happy women were faster and more accurate to detect. Does the effect of one face affect the next face? So here, there is in accuracy a kind of priming effect that happens where if an angry face, so the prime face is in the rows here and the target face is in the columns. So the easiest place to see this is when you look in the column for the happy faces. If a happy face shows up after an angry face, it reduces accuracy by 1% percentage point relative to if it follows the happy face. And so that would, so in some sense, happiness is priming happy, making you more accurate than if angry shows up beforehand. There's other ways we could explain that. I don't need to spend too much time on this. This is just to show you that accuracy and reaction time can actually generate two different effects. So if we just stopped at accuracy, we might have the wrong idea. But now if we look at reaction times, turns out that an angry prime speeds up the ability to say happy. And a happy prime slows it down. It's as if once you've processed the angry face because you've already seen anger, happiness is a stronger signal. And so I include this simply because I want you to be aware that we're going to be doing some things with reaction time in the Open Sesame study, with accuracy in the signal detection study. We'll probably do maybe some reaction times there too. And that these things can either work together like they did with angry men being both more accurately detected and more rapidly detected. But you can also have here reaction times and accuracy showing different effects. And the more statistically significant effect, these accuracy effects are really very small, right? These reaction time effects are quite big. And what we want to do is we want to figure out some way to take the statistically significant results here and make sure that they are not explained away by the patterns over here. If this accuracy effect is not statistically significant, but the reaction time is, then we can think that the reaction time, it's not that the accuracy is counter explanation to the inferences we're making about a contrast effect in the reaction time condition. Now, I suspect that I've gone a little off the path here. So don't worry too much about reaction time right now. You're going to be learning how to collect reaction times, but it's not until we get into the in-person classes that we'll really focus on thinking about speed accuracy trade-offs. So just retire that for right now, and let's go back to thinking about accuracy and signal detection. In this case, when we ran this study, I was originally looking for those priming and contrast effects, but the bigger effect was the interaction of gender and expression. Huge, huge effects. And so we replicated it again and again, and that became the paper that we wrote. Even though initially we were looking for one set of effects, when you see some really big effect that's never been observed before, then you change you change your focus and you start designing experiments to bend over backwards to first replicate that, make sure that effect is real. Then you come up with counter explanations for it, and you try to manipulate things and see if you can make the effect go away or if you can attribute it to some other explanation. And so when we get to the in-person part of the class, we're going to be talking a lot about how over the course of 20 years of my career, we've gotten a really good sense of the speed and the accuracy with which people process threatening and threatening information and opportunities as well. So now I want to take a break, but I will stop sharing. I just want to ask if there are any questions real quick. Okay, let's take, oh yeah, go ahead.
Sorry for taking so
No
long.
problem.
I have a question about the manipulations because we usually see that there are always evidence for the outgroup, or the manipulation usually uses the outgroup of a black person or a person from an ethnic minority. Are there
Right.
any researches or evidence that or manipulation that they use the Caucasian face as the outgroup? And again, if the results are replicated.
Yes. So this is a great question. Can you just flip this around? So one of the things we did, at Arizona State University, there aren't that many black students. I think in the general population of the United States, it's about 12% that are of African origin, and at ASU, it's about 5%. So we're a place where you can instantiate black faces as the out group. But if you go over to Florida, where my colleague John Maynor works, then you've got a 50-50 split. So we replicated some of this work there in an attempt to show that if you're surrounded by more of these folks, then maybe you can get the effects to reverse. So in the black participants, yeah, they show these effects for Caucasian faces. We didn't have enough in our sample to look at that, but John did. Now, the surprising thing was that overall, there was still a bias to see the African faces as more threatening, or generating these biases that we think are about aggression avoidance. And Liz Phelps at New York University also did some research that found a similar thing. She was looking at the implicit association test, which many of you are familiar with. And this is a task where you see words that are good or bad, and then you see faces that are black and white, and you look at how people push these buttons and how fast they are and how accurate they are. And it turns out that when the buttons for black and bad and white and good are the same, people are faster to make decisions than when it's white and bad and black and good. And so that is a way of identifying the degree to which we implicitly associate the outgroup with uh, negative consequences. Well, when Liz Phelps did this, she had equal numbers of black and white participants, and she did replicate that white participants are often associating black faces with negative words. Um, but when you look at the black participants, they showed two different patterns. Um, some of them showed this wariness, this outgroup vigilance for white faces, but some of them showed it for black faces. And she inferred that this was really a function of how aware these black participants were of the stereotypes. So it wasn't that they were prejudiced against themselves, they were aware of the stereotypes. And so pressing that button is a function of this social knowledge that they had, not of a bias. So we have to be careful about that too. If I give the implicit association test to my colleague Steve Newberg, who's one of the top researchers in the world for prejudice and stereotyping, because of his awareness of all of the literature on this, he might show those same kinds of biases, even though I don't think he's a biased individual at all. He's really done his work in not being a prejudiced or discriminating or a discriminative individual. But because he studies this, that association is built up just as a function of studying it. So we have to be careful about the implications that we draw from these biases. But we also can be relatively confident that a lot of people, when they show these biases, we're seeing biases that then can be predictive of bias performance in other criterion validity type scenarios, like a person who's got a high IAT bias against blacks might, in a human resources circumstance, be less inclined to hire those individuals than a white participant. But yeah, back to your question, it really isn't about black and white. It's about what you think of as the outgroup. So when we go to India and we do research there, well, skin color isn't as much of a thing. It actually is, but they don't think it is. And so we haven't done these studies yet. But what we have done is we've done things where people are discriminating in group and out group based on the facial hair that men have, because you can tell Hindu from Muslim with the way that the facial hair is cut. And so we can, at least with male faces, see these in-group and out-group effects, and they totally flip. If you have Muslim participants, they have the bias against the Hindus. If you have Hindu participants, they have the biases against Muslims. And my suspicion is that you could go all around the world, and what we're really talking about is a Stone Age mechanism, an evolved mechanism that is designed to be vigilant about people that don't belong to our own group, but that there's nothing about race or ethnicity that's that is itself instantiated in the way that we perceive things. That's socially learned. You have to learn who the in-group and the out-group is. When we get to the in-person classes, we can talk more about this, because I have actually a richer set of possibilities that we could get into, but I got to show you some other empirical results first. Other questions? Okay, we're going to take a 5-minute break. When we come back, actually, let's make it 10 minutes. When we come back, we are going to go through a basic signal detection calculation, which will prepare you to then, for your first or second assignment, I don't care what order you do it in, do a signal detection assignment on the memory data that you just completed. But some of you haven't completed those surveys yet, so we'll wait to dig into that actual data. Or maybe I guess we can use an older version of that data set, and that way I don't have to wait for all of you to finish it. But yeah, let's take 10 minutes and I'll see you in just a few. Ooh, okay, I'm ready to pick up again, and I've started recording again. So now I want to take a little digression. I've been talking about these signal detection parameters of bias or criterion placement and sensitivity. I want to show you how to calculate this. So we're going to jump over to, let me share the screen. We're going to jump over to this Excel worksheet here. This is a study I did many years ago, and we'll probably play around with this a little bit more, but this is similar to what you saw already. I've not actually ever published this one. There are angry and happy male and female faces. So I've got the first two columns are the angry targets, second two columns are the happy targets, females and then males. And what we've got here is we've got a discrimination problem, right? You are trying to discriminate anger from happiness. The male and the female nature of the targets shouldn't make a difference. Or at least the conventional wisdom in the late 80s, early 90s was that shouldn't make a difference. Probably through the 90s, actually. We didn't publish this until 2007, but there were other people that were starting to see evidence of it. I think we first saw it in 2003. So the task is straightforward. You see a face, you indicate whether it's angry or happy. And so each subject gets their own line, and then we aggregate over the trials in three different blocks, block 1, block 2, block 3. So you can look at changes over time. And then I also have male and female indicated by the numbers 3 for female and 2 for male. There's a lot more females in this sample than males, so we can't really look at sex differences. It's a very unbalanced design. And then one person declined to share gender or was non-binary in this study. So we will ignore session as participant sex, but we'll ignore that. What I'm gonna do is I'm gonna aggregate the accuracy across these three different blocks. So we're gonna work with this part of the table here. Now, what do these numbers mean? Well, for the first subject, number 76, when the target was female and it had an angry expression, 93% of the time they were accurate in detecting it. When it was a male, 93% of the time they were accurate detecting the anger. When it was a female target with a happy face, 93% of the time again. But when it was a male target with a happy face, only 80% of the time were they detected. What happens in the other 20% of trials? What are they doing?
Instead of false alarm?
That is a false alarm. And the false alarm would be it's a happy face, but they call it angry. So that's a key thing. We need to think about what we want to call our signal and what we want to call our noise. So let's make anger the noise, detecting anger. Actually, let's make happiness let's make happiness the signal and anger the noise. Let's say this is a happiness detection task. It's arbitrary, and all it's going to do is it's not going to change the calculations. It just changes the way that the graphs will be oriented. Yeah, so let's say that happy is the signal and angry is the noise. So that means that these are hit rates. And then here, these can give us false alarm rates, but it's 1 minus whatever these are to give us the false alarm rate. So in order to transform these into signal detection metrics, well, I mean, the first thing we can do is we can do this. Let's just look at what our patterns are. Equals the average. And I select all of these. So I'm 95% accurate. Participants are 95% accurate detecting happiness on a female face, 89% accurate detecting it on a male face. And if we take these accuracies for anger detection, we could also look at 1 minus those and we'll get our false alarm rate. So false alarms are 12% of the time when it's angry on a female face, they're calling it happy. So that is a false alarm to say happy even though angry was there. And only 10% of the time on a male target that's going to be happy. Or they're going to be calling it happy. Probably not a statistically significant difference between those two, but this is a within subjects design. So we can actually ask that question and answer it statistically. Maybe a more interesting one that's more likely to obtain is to look at 95% versus 89%. Are people more accurate detecting the happy targets when it's a female face versus a male face? Well, because these are all the same participants, we can actually just craft a difference score here equals the happy target minus the happy target for female faces minus the happy target for male faces. So that difference is positive in this first case, and we drag this down, and we can just scan across and we can see that it's almost always positive. It seems like almost everybody is more accurate with the happy targets than with the female happy faces than the male happy faces. There's one person here who's got it going in the other direction. That person, by the way, has some other issues too, but we'll leave them in the data set for right now. Okay, so here's a vector of difference scores. And we can also look at what the average difference is. It sure should be 6% because this is just a different way of calculating what we calculated over here. So that 6% average, is that statistically significantly different from 0, which is the null hypothesis? The null hypothesis here is that there's not going to be any difference in the accuracy for happy detections on a male versus a female face. And so in order to test that, we just do a one sample t-test equals this average. So we put the average in the numerator, the average difference score, and then we divide by the standard deviation, the spread of this. And if we stopped at this point, the average divided by the standard deviation gives us a Cohen's d. Our Cohen's d is 0.67. That's a medium to large effect. So even with a small sample like this, we're probably going to have a significant t-test. So this is the average difference. This is the Cohen's d. And the t-test p-value actually the t-test is what we're going to get here, not the p-value, is this average in the numerator divided by open parenthesis. We first want the standard deviation, just like we did. But to turn a standard deviation into a standard error of the mean, we divide it by the square root of the count. And you may remember this, but if you don't, rest assured that most of the people that I teach don't remember how to do a one sample t-test by hand off the top of their head. So no worries. If you do this a couple of times in your homework assignment, you'll start to get it and you'll generally remember it. So I think that this is right. Our t-test is 3.28, and we can get a p-value for that equals, I think it's t inverse. I don't know why I always forget this. No, it's t distribution. Here's x. The degrees of freedom will be the count of these values minus 1. And then we'll do a two-tailed test, even though I can do a one-tailed test because I've found this effect so often that I can make a directional prediction. We'll just do a two-tailed test here. So even with a small sample, we have a significant t-test with a p-value of 0.003. That's less than 0.05, our alpha criterion. And so we can reject the null hypothesis and say that people appear to detect happiness more accurately on a female face than a male face. But this is just looking at accuracy. We can do the same thing for the false alarms. Are the false alarms higher for female, for saying anger is happiness on a female face versus a male face? We do exactly the same thing that we did over here. This minus this. There's no difference for the first participant. We drag this down. Seems like there are some negatives and some positives. We can just copy and paste all this stuff here. It'll update, so I'll get the same exact, the same exact set of operations I just copied and pasted. So there's a negative 0.02 difference. The Cohen's d is negative 0.2, which is a small effect size. And then the t-test is coming out as -1. And then the p-value can't calculate the t-test because in Excel, for some reason, they only allow positive values for the t distribution. So we just have to change this and say absolute in this formula. All of this will be covered in a more detailed video for your homework that you can watch. But the p-value is 0.32. So we don't reject the null hypothesis that false alarms are higher for female targets than male targets. But, we could have specified things differently, right? Maybe we said that the angry faces were the target and the happy faces were the noise. And then we would be looking at false alarms to happy faces. We'll just drag this across. There's 11% false alarm rate to call a happy face angry if anger is the signal, relative to a 5% false alarm rate for female faces. So 11% for male faces, 5% for female faces. I don't think I have to show you that this difference is going to be exactly the same t-test as this difference was. So in that respect, there is a false alarm effect. It just depends on how you define what your false alarm and signal, what your false alarm and hit is, and that's a function of what you call the signal and what you call the noise. And it's based generally on the research question that you're asking, but there's nothing dodgy about switching those if it makes it easier for people to understand. All right, so this is what we do with accuracy and false alarm rates. Now let's do something with signal detection metrics proper. So the first thing we're going to do is we're going to copy this over here. So I've got a new workspace, and instead of copying over these hit rates and false alarm rates, actually, these are all accuracies, so we'll change it to a false alarm in just a moment. What I want to do, since happiness is our signal, I'm going to say equals norm S inverse, open parenthesis, and then I put this probability here. So norm S inverse is the thing that turns this into a z-score. So remember from Monday's lecture, the normal curve has all of these nice properties, and one of them is that mathematically we know exactly the percentage in a perfectly normal curve of the scores that lie above a particular point in terms of the standard deviation, z-score. And by converse, we can take the proportion of things that we're seeing in a tail of the distribution, or in the hit. In this case, it's 93% of the distribution is correctly being detected as happy for female targets. And so we can turn that into a z-score with this norm S inverse. And so that gives us a positive 1.5. That's for happy faces that are on females. We can drag this over, and so for 93% of the distribution, that's a z-score of 1.5, positive 1.5. For 80% of the distribution, that's a z-score of 0.84. So as the number goes down, the z-score goes down. Now, as I try to, so I can take this formula and I can copy it by taking this white crosshair and turning it in and putting it on the lower part of this highlighted area until it becomes a black crosshair, and then I hold my button down and I drag, and this will fill in the same formula in all of these cells, but it'll update the cell reference. And something bad is going to happen in a moment, so don't be shocked. Okay, so we've got a lot of those numbers, but the bad thing is that we've got this happening. Norm S inverse, if I highlight this, it tells me where the reference is. The norm S inverse of S16 cannot be calculated. The reason is because the normal curve goes out, the tails of the normal curve go out to infinity. And so there's actually no way to have 100% of that curve. So you can't have your z-score would be infinite. You could have it, because obviously we do have it here. So what we need to do is we need to modify all the ones to be slightly less than 1, and all the zeros to be slightly more than 0. And the way I'm going to do that, there's a couple of different ways that we can do it. We can do it in code, but I don't want to confuse you with complicated formulas. So the way that I'm going to do it is I'm going to take this and copy it, and then so these are all formulas right now. Now I'm going to paste the values in there. And now I'm just going to Control H, and I'm going to search for anything that says 1, and I need to make sure I match entire cell contents. And I'm going to change that to a value that's halfway between perfect performance and 1 wrong. 93% is 1 wrong, and so halfway between that, we'll call it 96.5. Let's just round it up to 0.97. When we publish things, we'll be a little bit more precise in how we do this calculation. So now I've changed all of my ones to 0.97, and I've gotten rid of that problem that I had. It's also going to be a problem with zeros. But I think we've just taken care of that too. So, okay, close. So now we need the false alarm rates. We need to make z-scores for false alarm rates. These are the hits. These are the false alarms. So we're going to take this formula and we're going to paste it here. But in order to turn this into a false alarm, remember it's the complement of the accuracy. And so we really need this to be 1 minus whatever the value is in S13. Actually, no, we need this to be not S13 there, but Q13. There we go. So not surprisingly, if 93% is generating a z-score of positive 1.5, 7% is generating a z-score of negative 1.5. We'll drag that across. We'll drop that down. Now we have all of our false alarms as well. And now we can calculate D prime. For female and male targets. And we calculate it very simply. Actually, before I go on, I want to make sure that everyone is aware of where we're at right now. Are there any questions? Because what I just did here is I put that 1 minus in there, and that can easily escape you. So really, I should maybe make a new column of false alarms equals 1 minus this. These are the false alarms. To call an angry face happy. And these could, instead of referencing 1 minus Q13, we could just reference this cell. That won't change anything, but I hope it makes it a little bit more clear what I just did. Are there any questions about how I've got to the z-scores? Okay, D prime is defined as Z for the hit minus Z for the false alarm. So the calculation for D prime is going to be very, excuse me, very simple. This hit rate minus this false alarm rate. So it's 3. And I can drag this down. And then I can center this white crosshair over the bottom of this, turn it to a black crosshair, drag it across. Now I have my D primes. What is D prime? D prime is how far apart the modes of the signal and noise distribution are in units of z-scores. And since z-scores are these standardized measures, it allows us to compare across very different tasks. So in this task, we could compare this discrimination task to how well they can discriminate male from female, and we could look at the D primes, and they're going to be in the same units. And so it allows us to say, perhaps, that people are better at discriminating masculinity and femininity than they are at anger and happiness, or vice versa. Now, the other thing we can do, I'm going to move this down here. And I'm going to move this down here. We can look to see if people are more, well, I mean, the first thing we can do is we can calculate the average. So let's put that up here. So the average is 2.89 for the female targets, 2.68 for the male targets. We could ask the question, are people better at discriminating expressions on female targets than male targets? And that just is going to be a difference score equals this minus this. So again, we take a complex repeated measures design and we reduce a hypothesis test about whether people are more sensitive to the expressions being made by female faces than they are to the expressions being made by male faces. We can ask that question and we can answer it with a one sample t-test. And we use exactly the same formula that we used over here. So I can just paste that in and I don't have to recalculate it. So it looks like we end up with a kind of low Cohen's d. It's not that strong. And the t-test is 1.59. And so that suggests that, yeah, maybe there's a trend in the direction of people being more sensitive to expressions on female faces, but we can't really reject that null hypothesis. Now let's do bias. Or more formally, this is Macmillan and Creelman's C for criterion. What is bias? We take the same calculation and we modify it as follows. Rather than subtracting the false alarms from the hit rates, we're going to add them. Well, now we're adding 2 z-score units, and so we need to put it back in the original metric of z-scores by dividing by 2. That gets rid of the units. That's the formula that we want. And so here, for bias, I'm going to take this, I'm going to add this, and I'm going to, so I've taken the z-score for the hit rate, I've added the z-score for the false alarm rate, which is negative, and then I divide by 2. And the value that I get here is 1.1 to the exponentiated negative 16. And so what that means is you have to add 16 zeros to the beginning of this. It's a super small number, very close to 0. This is just Excel not being able to, it rounds, it carries this math out to a very, large number of digits, but this is essentially a 0. When you see numbers like this, don't panic, is what I'm saying. We'll drag this across, we'll drag this down. We could change all of those to zeros. Sometimes it does calculate 0 correctly, but other times it doesn't. All right, so here's our biases. Let's look at what our averages are. What our average biases are equals average So there's, for the female targets, a bias 0.17 is a positive bias, and that's a positive bias to say signal or to call faces happy. We drag it over to males, and it's a negative 0.04157. So that means there's a slight negative bias to see male faces as angry or a bias away from seeing them as happy. So a positive bias here. Now, the nice thing is we can also do a one sample t-test on these biases. So is there a significant bias to call female faces happy? We do average of all of these divided by open parenthesis, the standard deviation of all of these. And if we stop there, that we would have Cohen's d, but we don't want to stop there. We want a t-test. So we divide by the square root of the count. And close paren, close paren, close paren. That's going to give us our t-test. And that's a big T, and our p-value is probably going to be less than 0.0. Let's see, here we had a t-test that was, we'll figure out what it is. We can take this and copy it. Our p-value is p of about, let's say p of less than 0.003. So that's the bias for females, and it's really testing against the null hypothesis of zero bias. If we drag this over and do this for males, well, they're much closer to zero, so we're not going to get a bias. We don't have a t-test that's significantly different from zero in saying that men have a negative bias, but we can do another test, which is the difference between these two. This is the simple effect of bias to female versus male targets. So there we go, this bias minus this bias. You can do it the other way around too, but I know that that would generate a negative number, so I'm not going to do that. And then we can take this t, we'll just copy all of these over here, get rid of this. So that's a t of 3.36 and a p-value of 0.003. So we can talk about the results, the biases that we see in two ways. The take-home message really is that expression is not independent of the gender, the perceived gender of the face. And so if you think a face is female, you have a significant bias to say that that face is happy, which means that sometimes an angry face shows up, but you still call it happy. And that doesn't happen with male targets. In fact, there's a slight tendency for the males to be false alarmed more as being angry. So even when they're happy, they're seen as angry. And in other data sets, I will, in fact, observe this effect more. So it just depends on how you run these analyses. We see sometimes that biases to see females as happy is the stronger one. Sometimes the bias to see males as angry is the stronger one. Now, one last thing I want to do here. I have this worksheet that I can share with you, and all of these things are laid out in a much clearer way, I think, on this next sheet. But it turns out in this study, we also looked at reaction time. So I have all of these accuracy measures, but I have reaction time too. So let's just look briefly at reaction time. We measure reaction time in milliseconds. So this is 798 milliseconds. Here's 999 milliseconds, so almost a full second. We can average across all of these, and we can generate a sense of how fast people are performing these decisions. Now, these are reaction times for accurate decisions. We do not have reaction times for false alarms, but we could get those. I just didn't create them in this spreadsheet. And when we look at this, what we see is that in addition to there being a bias to see female faces as happy, when a female face has happiness, people are faster to detect it than when happiness is on a male face. And people are faster to detect anger on a male face relative to a happy or relative to a female face. Are these differences significantly different? Well, we can do the same kind of thing that we did on the other sheet. We can create a difference score. Now we don't have to worry about z-scores at all, though. So I can go equals average. Let's test whether anger is detected faster. So I'm going to do on a male face versus a female face. So I'll do the average of these angry male targets minus the average of the angry female targets. And yes, I want to. So that gives us the difference, and we scan and we pull this down and we look across these numbers. Lots of negatives, some positives. We can make this look a lot prettier by reducing the number. There we go. And we can do the exact same thing that we did and generate a t-value equals average of this vector divided by the standard deviation. And we have to put that in parentheses because we need to turn that standard deviation into a standard error by dividing by the square root of the count close paren, close paren, close paren. And that gives us a negative t-value of negative 0.633. That t is less than 1. And so that even though there's a reaction time difference apparent in this graph, it's not a significant difference according to what we just calculated. Of course, we do have some funny values in here, like this 650 millisecond difference, or this thing that can't even be calculated here. So there are some things we can do like trimmed means, and it turns out that if you trim the means using Rand-Wilcox's robust statistical approaches, one of the ways you can do that is it just corresponds to removing the highest and lowest score. So I remove that lowest score and this highest score here. That doesn't do anything. We could remove the next lowest score, which I think is this one. Nope, that wasn't it. Oh, that is it. Yeah.
I think there was a higher score.
Oh, there
Yes,
was?
that one.
Ah, you're right. There we go. But still, none of this, even robust statistics aren't picking up that there's a difference here. There's just a lot of variance in this. So we'll Control Z and put those things back. So I just wanted to show you that we can not only generate these, senses of how the accuracy looks, but we can look at reaction time. And here we're seeing that people truly seem to be more efficient with the female happy faces relative to male happy faces. Okay, so that is what I wanted to do with this worksheet. Let me see if there are any questions. For your homework assignment, I'm giving you a different data set, and I have another video that explains how to go through it. So you'll have access to this video plus another video.
I have a question.
Yes, Naomi?
Yeah, so can we start working on the worksheet that is in Canvas, published on Canvas already? Or will it be another worksheet?
I think that you can start working on it, but I tell you what, give me a chance to verify. I was going to give you your own data set. And so just let me verify that the one that I've got up there, which is a greater number of subjects, that I've got the right video to do to work through it. So don't move on it until I'll send an announcement out. It's not due until I think I made it due May 3rd or something like that. And really, I just wanted to give you due dates to kind of like keep you going through this. What I'd rather you do with the interim time is, I mean, in many ways, I would say the thing you could start on right now is the Open Sesame tutorial. You can
Okay.
have that done in 4 hours. And then move on to this, and that'll give you two tools coming out of this expert workshop that really are, I mean, these are incredibly powerful tools. You're going to know that you can program and design experiments with a computer, and you're going to know how to transform things into these signal detection metrics. And, how many other expert workshops do you take where you get two practical tools like that? Um, what I what I what I do want to do though is, with the the homework assignment version of this, what we're doing is instead of a perception task, it's a memory task. So you had an experiment where you saw faces and you saw information that said either they had a disease or they didn't have a disease. And then you have to remember whether they had a disease or not. So memory can also be a signal detection task. And here, there's a real truth of the matter as to whether the person was presented with information about having a disease or not. But you could be biased to misremember when you see a male face versus a female face. Maybe we are more biased to think that men are going to have a disease. And there's a couple of other things in that data set too. So just give me a chance to check it out and
Sure.
verify that what I've got up there is going to work.
Sure.
Any
And
other
then I have
questions about?
another
Go ahead.
question. So for the different tab you were in, so not reaction time, but the hit and false alarm rates and C-scores. So we are creating graphs of this, right? For the assignment.
Yes.
So are there any things we should take into account when making these graphs? Do you want a bar graph, for example, or graphs on, yeah, I don't know,
Well,
the
there's a number of different ways you could tackle this, right? We could generate a bar graph. Uh, and that's particularly easy with these numbers up here. You could just generate a bar graph of the accuracies for these decisions. But whenever you get into the signal detection metrics, you end up having, well, for D prime, as long as people are doing reasonably well on the task, it should be well north of 0. So running a t-test on these things doesn't make any sense because the null hypothesis is that you'll have 0 sensitivity, and we sure hope that people can tell these things apart. And in fact, we get a t of 17, a huge t-test. So this hypothesis test isn't that interesting, but plotting these things against each other is quite interesting, right? But now you don't have 4 bars, you have 2 bars that you'd want to do. You'd have female and male target. And we just take this and insert maybe a bar graph. Maybe you'd want to do a line graph. And make it pretty and do cool things with it. You can also move this into, y'all are still learning Jamovi or R. You can run all of these things in R too. I'm showing you how to do it in Excel because it's a hands-on kind of approach. Now with bias, I also like using bar graphs, but sometimes I'll use line graphs instead. And with bias, the nice thing about these graphs is that here the 0 really does mean something. So you can see a positive bias for females and a negative bias for males. That's an ugly graph. I'd need to fix that and make it look pretty. So that's how you might do it. You might end up having 4 or 5 graphs. So just play around with it. Think about everything in this class as producing something that you can use in a portfolio to get a job. So don't just answer the questions, but make it look pretty. Make it look like something that you can show to a prospective employer and say, look, I not only know how to do signal detection analysis, I know how to present it. Any other questions?
Is it possible to also have 4 bars? Because I was thinking it would be nice to also have visualize like the hit rates or false alarm rates across the 2 by 2 design as well.
Yes. Yeah. So I absolutely can do that like I did with the reaction time. I could um I could look at false alarm rates or I could look at hit rates. But generally what I have to do there is I can put female and male target in the columns, and then I want to do angry and happy. And for the angry ones, we'll go there. For the happy ones here. Nope. Drag these across. And this chart makes a lot more sense when you're looking at this reaction time chart, pairing them side by side. I'd want to make the bars the same color too. Um, so that would be, one of the things that you'll end up discovering is that we really, even though it's kind of redundant, we really do want to run analyses on hit rates, false alarm rates, D prime, and bias. Each one of those gives us, even though they're related, they give us slightly different ways of viewing what's going on. And so this is a place where there's a lot of different ways you can do this assignment. Um, so feel free to explore. Any other questions?
Yeah, I had a question about the Open Sesame tutorial.
Yes.
So in the syllabus, it says that we have to send in a video of how we modified it. So just a video of the final result or the process of modifying it.
I'm sorry, I must have missed. What's the question?
So in the syllabus, it says that we have to hand in a video of how we modified um, the,
Yes.
yeah. So do we have to hand in a video of like how it looks in the end after we've modified it, or the process of
Yes.
us modifying it?
Yeah, here's the problem with the Open Sesame is that you'll create an Open Sesame experiment, and if you upload that and send it to me, then I've got to open Open Sesame. And um, depending on there's something about different platforms that makes it challenging. So what I really want is I want to be able to evaluate what you've done. So you're going to go through the tutorial and you're going to make some kind of change, right? So let's say you go through the tutorial and you say, okay, well, right now I have to upload these happy, or I'm sorry, this face that looks to the left or the right. I'm going to modify it and I'm going to make it a happy face looking to the left or the right. Or I'm going to modify it and change what the peripheral task is. They're no longer looking for letters, they're discriminating the color of a letter. Uh, you have to make some sort of change to show that not only can you do the tutorial, but that you've also been able to modify it in some way that's unique. In the past, I just had people do the tutorial, and then I wasn't quite clear on whether people were just, they had one person do it and then they just shared the result among them. So this way, everyone does something a little bit different. Uh, it can be a little different or it can be a whole lot different. I had one person last year replace the central target with animals that were either oriented to the left or the right. They changed what was happening on the sides where there was not letters, but additional pictures of food, I think is what they did. And so they basically, by the time they finished the Open Sesame tutorial and modifying it, they had a full-blown experiment that could be done. They could run it on other members of the class. And one of the nice things about these studies, which I hope you'll see from this data set, is you can run 20 or 30 participants. And because you're leveraging the power of within subjects designs, you can get highly statistically significant results. even without, running a bunch of subjects. You all have to do a master's thesis, and many of you will run hundreds of subjects to try to get some sort of between subjects difference, right? But with a cognitive design like this, you can run 40 subjects, and then when you find some effect, you can run another study with another 40 subjects, and then you can run another one with another 40 subjects, and you can basically, I think it's just a much easier way to do replicable science when you've got the capacity to not only find an effect, but then replicate it several times and use different manipulations to kind of bend over backwards to disprove whatever your pet hypothesis is. So in the case of angry men and happy women, the first alternative hypothesis that we came up with was, well, maybe there's a stereotype that men are angry and women are happy, and that leads to this bias. So we designed an experiment in which we measured those stereotypes using an implicit association test. So now we had a covariate that gave us a sense of how much people associate men with anger and women with happiness. If you include that covariate in the statistical analysis, it should wipe out the effect. In fact, it didn't change it at all. So it didn't seem to be stereotypes. Well, then we thought, well, maybe it has to do with the fact that men and women just learn to make these expressions more vigorously. So we did a few other things. We took computer-generated faces where we could really control the degree to which the expression was made. And we still found the effect. And then we did some things where we put on clothing that was masculine or feminine on a gender-neutral face. And we showed that the stereotype of the clothing didn't drive the effect, but manipulating something physiognomic did. And so the moral of the story is not only do social cognition experiments vastly increase our ability to make inferences about what's going on inside the social perceiver, inside the social rememberer, inside the social judger, but they give us methods that are far more rigorous than are typically seen in social psychology, or were typically seen in social psychology. And they often can give us methods that, even if you find a surprising result that you didn't expect, you can then replicate it multiple times, and you can really start to be sure that you're not dealing with some kind of unreplicable study, which is what got us into the social science, replication crisis in the first place. The people that got us into that situation, sometimes they were social cognitive thinkers, but in retrospect, almost no one in cognitive psychology had studies that didn't replicate. And many of the social cognitive methodologists who use these methods well, like me and my colleagues, we survived the replication crisis quite nicely. So the replication crisis really arose from sloppy uses of these methods or not using these kinds of methods at all. Another moral of the story is, with these, you can find an effect and then you can replicate it and you can replicate it again. 3 replications, and you're probably dealing with a real effect that generalizes to all sorts of other places if you use the same stimuli and the same experimental designs.
I had a more technical question about the Open Sesame tutorial. Is it the one that can be found on the website of Open Sesame? Is
Yes.
that the one you're referring to?
Yeah. And it's replicating a study called I think it's The Eyes Have It is the name of the original paper. But it replicates a very widely done study. But by the time you're done with it, the reason I like it is because it's really straightforward, aside from some of the bugs. Like at one point, I think one of the things that will happen is you will put a piece of text up and then you won't be able to see it. And it's because the default font color for the text is white and the background is white. So that's one mistake that that's one bug that will happen. But I never know because they changed the tutorials and they changed the program. Now they've got this AI assistant, so hopefully there won't be too many bugs. But yeah, it's the first one, and by the time you're done, you've designed a chronometric attention paradigm that's actually far more sophisticated than the studies that we're looking at here. You know, you could easily, by the time you're done with that tutorial, you can easily replicate this study because this is just popping up a face and getting a keyboard press. You don't have to have a schedule where first you have a face appear and then letters appear on either side, and you counterbalance the order that they appear. This study, this anger and happy detection could be done very easily in Open Sesame once you get that initial tutorial done. So I really envy you the discovery of this. You don't even know how powerful your intellectual curiosity can become whenever you have methods like this at your disposal. It's really beautiful. Okay, I just want to close today by jumping back to a couple of ideas. So here, from the current slide, there we go. This is, whoops. This is a figure from the chapter on social inference that I wrote with Klaus Fiedler and Christian Ukelbach a few years back. And I just want to point something out. And I said this on Monday too. When Sherlock Holmes says it's deduction, Watson, he's actually incorrect. When a detective takes clues and infers a cause from those effects, they're using abductive inference. So with deductive inference, we have a rule, all men are mortal, a case or a cause, Socrates is a man, and we infer the effect or the outcome, Socrates is mortal. And if the rule is true, then deduction is always true. Inductive inference would be observing lots of men, seeing that they all die, never seeing a man that doesn't die eventually, and inductively inferring that all men are mortal. So you get a rule out of a series of cause and effect relationships. This is what we do with statistics. And it's possibly, even probably true, but that's why statistics is always a game of confidence. We might have a p-value of 0.003, which says that only, 3 times in 1,000 would you see an effect like this if the null hypothesis were true by chance alone. It's still possible. So induction has degrees of statistical certainty. Abduction is often thought of as an error. It's called, it's a fallacy in many ways because, logically, if you have a rule, if P then Q, and you get P, then you can infer Q logically. But if you get Q, inferring P is a mistake. It's called affirming the consequent. And we don't want to do that if we're doing deduction. But in fact, most of social cognition is exactly that kind of thing. And most of social cognition is open to making mistakes. I come home late from work. I see that my romantic partner has a cross look on her face. I infer that she's upset because I'm late getting home from work, but I could be wrong. She could be upset because she just got off the phone with a friend and something happened. I could be wrong in the opposite direction. Maybe she expected me to be late and I showed up earlier than she expected and she's not ready to see me yet. So she's cross about that. There's all sorts of inferences that we make about what causes the social signals that we see in another person and we can always make mistakes. But like good detectives, there are some things where we just really make rapid process one kind of inferences. Those are called overcoded abductions. So automatic or implicit things like stereotyping. We're walking down the street, somebody comes out, they're an a young, athletic build outgroup male. We cross to the other side of the street just automatically. We don't even really think about it. But other times, we want to engage in a more diagnostic, or I would say forensic kind of abduction, like a detective, like Sherlock Holmes. You come home, your partner has a cross look on their face. You say, hey, what's wrong? You ask a question. You try to get a better sense. And the more evidence you gather, the more you're able to converge on what the actual cause is. In our lab, we have this model of the fundamental motives. And so these are this is a figure that did not make it into Becker and Newberg 2019. Grabbed this from an old version. We'll write a new paper. Yeah, let's call it Becker and Newberg under review because I got to put a new paper together and use this figure. I like it so much. So we have three big domains of fundamental motives. People need to survive, they need to reproduce, and less often studied in evolutionary psychology, we really have motives to thrive. But those are really big goals, right? We find that it's much easier to focus on more specific goals and contrast them against each other. And these goals emerge at different life stages. So for an infant, they just are trying to avoid being deprived of resources, and they're trying to get, more resources. Once you become a child and a toddler, a child and a prepubescent child, you start to pay attention to other things like avoiding aggression, not being cheated, and you do a lot of playing and you learn a lot of things from your parents. And then as we get into post-pubescent realms, that's when reproduction turns on. By that point, we've been striving for status in our social groups. We've learned how to trade. We've built coalitions. And within a domain like reproduction, we see a series of related goals. You first need to acquire a mate. Once you do, you want to produce offspring. And then when you do that, you want to continue to hold on to your mates, make them happy because it helps split up the child rearing, and you want to nurture those children. Now, does everyone want to acquire mates? Does everyone want to have children? No. But we have these mechanisms that are designed for it. So even if we don't want to do it, we often have these things creeping in to the calculation. So a lot of what we'll be talking about in the future is about these fundamental motivations. And I'm giving you a paper that overviews what we've done in the lab with this. Did I already give this paper to you? I'll look and verify. You don't need to answer the question. So what you're going to be graded on, actually, I'm going to skip out because this slide is incorrect. We'll back out of that. I want to give you examples here. So eventually what you're going to do is you're going to propose your own study. And what I'd really like, since the class is so big, is rather than write a paper, I would like you to go into Open Sesame or use Qualtrics. I'll show you how to use Qualtrics to do this as well. And I want you to design a social cognitive experiment. And so you'll be producing a video of the Open Sesame, and then you can just post that to your YouTube. And if you don't know how to do that, you all have a YouTube channel as part of your Google accounts. Or if you don't, then just get one. It's super easy. You can just screen record what's happening, or you can even if you can't figure out how to do that, you could take some screenshots of what's going on and you could put it into a PowerPoint and you could just record the PowerPoint, narrate it, and then upload it to YouTube. So you're going to propose an experiment. and it's going to have all sorts of there's all sorts of possibilities. So I'll show you how to do a social memory experiment. That's probably the easiest one to do. You show people faces, you give them some information. Here are some men and women of the in-group and the out-group. Some of them are cheaters and some of them aren't. And then you show the same faces again and you try to figure out, did they cheat or did they not? And there you can easily have a situation where people could be very good at detecting cheaters in one group versus the other. Maybe they're good at detecting cheaters in the out group. They're more sensitive because they pay more attention. Maybe they show biases to think that in-group members are going to be trading with them, and so they have this greater propensity to miss cheaters of the in-group. I don't know. Remarkably, there is some literature on this, but I don't think it's very good. So every one of you could do a study on memory for social cheating, and we could probably get a couple of them done and have a nice JPSP paper come out of it. But look at the literature. I mean, I could be wrong. Maybe people have suddenly started doing this. 20 years ago, people did some work that I think is not very convincing. And then people just cited that for a long time, but that doesn't mean that it's right. So you come up with some idea, like a fundamental social motive, the need to avoid cheating. You then turn it into a research question. Do we remember cheaters accurately? Or are biases governed by some group? And then you design a study in which these faces are paired with descriptions of honesty or cheating. Now, you can do this with any of the motivations: status striving, ostracism, avoidance of ostracism, mating, self-protection. There's a lot of really good mating things that you can do. You think about the Open Sesame study. What if the face that's looking to the left or the right is attractive versus unattractive? Maybe we trust the attractive people more and we look in their direction more. You can also, I'm going to show you a lot of different other methods. So I don't want you to finalize your sense of what you want to research until we get to the in-person classes. We'll have 2 classes where I cover a lot of literature, and then you can design something over the weekend and bring it back or you can design something and pitch the idea, and then we'll have a final project. So I'm going to show you methods to figure out, can we ignore one social feature when responding to another? How easy is it for me to ignore gender when I'm looking at anger and happiness? How do we detect the quality of a dyadic interaction? What if we're looking at 2 people interacting with each other and they're romantic partners? Can we look at how they're looking at each other and tell whether they're getting along or not? That's a signal detection problem. Do we remember people better when self-protection is aroused or mating? There's some evidence for that. We can look at personality variables. Do introverts detect social signals of affiliation better? We've got some evidence of that from a project that actually came out of this expert workshop several years ago. Actually, we got 4 studies that have shown that. So there's an abundant number of possibilities, and every one of you can take your primary research interests and can turn it into some kind of social cognition experiment. So that's what we're going to be doing. You now know what your assignments are, but I think that what I'll do is maybe next week, I'm going to have office hours, and it'll be a little bit later. It'll be like 4:30 your time, so that I can get up at a decent time. And I'll have office hours and we can go over some more things if you're running into trouble. And I'll do the office hours around the same time. I think I'll do it at 4:30 because I think that we scheduled this so that this is when your other expert workshop is as well. But I'll post that in an announcement that tells you whether you can move on to the signal detection task as well. All right, are there any other questions?
So did I understand it correctly that then the other final assignments are the presentation and then designing the study?
Designing a study, and there's 2 options in the syllabus. One is that you write a paper about it. The other is that you actually design the study and do a video and show me that you've got the Open Sesame version or the Qualtrics version working. I would prefer that because it's a lot easier for me to grade that than 30 papers. But also, I think it's just a better demonstration that you have as a portfolio piece. If you go try to find a job or you go try to get into a PhD program and you can just show someone, look, I created this program. I know how to do this. It's much more valuable than you giving them another 10-page paper. So that's what I would prefer. But we can talk about it as things go along. Some people like to write papers. That's totally fine.
Okay, but we
Haven't-
should
Oh,
wait with preparing them until we've already met in person.
Yes, you should not be preparing it until we've met in person, unless
Okay.
you really already have a good idea, unless you're already saying, well, I want to do that social memory for cheating, and then get started on it. But I mean, work through the first two assignments first, and then you can start thinking about it. And if you've got time, get the Fisk and Taylor book, get the Kahneman book, get the non-Norman book, and scan those and see how these ideas are applied. Other questions?
So just to summarize again, we do the Excel assignment, the Open Sesame assignment, a proposal for an experiment, either in Open Sesame, Qualtrics, or write a paper about it, and a
Yeah.
presentation, right? Those four assignments.
Let's just stick with those first two because I was not prepared for there to be 30 people in this class, so I may drop one of the other assignments. I'm trying to figure out how to make this equitable because I don't get paid anymore. And it takes a lot of time to grade 30 assignments if they're the wrong kind of assignments. So let's just focus on the first two. And you have my promise that my goal in this class is for everyone to get a decent grade and you to come out with some really different skills and abilities, some new knowledge, skills, and abilities that you otherwise wouldn't have had. So let's not overly focus on grades and deliverables. Let's have the experience of learning this wonderful topic area and knowing that by the time we meet in person, you're going to have two skills under your belt that justify your attendance in this class already. And then we'll figure out how we close things out.
I have one last question, or I don't know if it's the last, but I was wondering with the Open Sesame assignment, um, maybe it's me, but I can't find the instructions on how to use the program. Is there any instruction on that?
Well, it's in a tutorial. So did you find the tutorial?
Yes, that's the video on YouTube, right? Or no?
No, there
Oh,
is there is a video version of it too, but if you just go to the place where you download it, find the tutorials, and the tutorials have not only a written set of instructions about how to do it, but also I think there's a video on how to do it.
okay, thank you. Then I guess I
If,
will find
if,
it.
yeah, if you can't find it by next week, I'll have some office hours, like I said, and we'll find it. Or just post in the discussion about Open Sesame. Where is this? But it's pretty straightforward.
Okay, thank you.
Okay, well, let's call it a day. I'm going to stop recording and